Okay. We're ready to go. Okay.
Hi, everybody. Good morning. Good morning. Hey. Thanks for coming. It's really nice to see you all. Thanks for coming. So this is a special day for Madeline, and to me too, because as you know, she's the first PhD student from the Neuro Music Lab, and I'm super proud of her today to be able to share with you all about what she has been doing in music perception and cognitive neuroscience research. And as you all know, she's a wonderful person as a classmate, as a colleague, as a friend, and then I'm going to add as a scientist. She's been going through tremendous amount of challenges. We've been through so much ups and downs, lots of emails, lots of brainstorming, lots of pilot data, scripting, bugs, glitches, malfunctioning, you name it. So she was there all the time, diligent, wonderful, graceful, and thoughtfully navigating all these things. And here we go. She's ready to swim away to the world outside. So I'm tremendously proud, and I thank her to be always a nice colleague and a big sister in the lab. And I thank you all to be supportive of her work, and as a whole kind of community, I hope she enjoyed the ride as much as I did.
Thank you, Takako. Okay, so my mic is on. Everybody can hear me okay? Okay. Thank you so much for that introduction, Takako. Thank you all for being here. Thank you especially to my committee and to Yarick for stepping in on the live stream, and to everybody else who's watching online. So today I'm going to share with you some of the work that I've done in the past 5 years as a member of the Neuromusic Lab, and it centers around an interest of mine in implied polyphony. I'll explain more about what implied polyphony is coming up. Hang on one second. There we go. And then we'll go through a series of 3 studies, the first 2 of which deal with the neural representation of whether or not there's 1 or 2 melodic motifs that are shared between implied lines, and the last of which deals with performers' expression and agency in expressing melodic discontinuities as they relate to pitch features of implied polyphony. And then we'll wrap up. Okay, so let's get started. Broadly, the acoustic scenes that we're confronted with on a daily basis are very complex. So you can imagine you're at the beach and maybe you're trying to hear somebody singing across from you. But that said, there's a crowd around you and some cars passing by and maybe some noisy waves on top of that. And that can be a very challenging acoustic scene. And in this bottom example, you have two musicians maybe that you're trying to pick out of a noisy crowd, and you're both listening to them at the same time and maybe potentially trying to listen to one or the other, separating those auditory streams. So to concretize this process a bit, we have these multiple sound inputs or potential auditory streams that are all reaching your ear at the same time. And it's the job of your auditory perception system to separate them into meaningful representations of real-world activities. And even discrete sounds, such as a single footstep, are similar enough such that our perceptual system links them into one coherent stream. Now, sounds that are linked together over time, right, can be based on a lot of different acoustic features, including frequency content, spatial separation, temporal envelope, as well as patterns over time. So if a pattern of sound repeats, there's reason to believe that it comes from the same cause. And successfully decomposing these auditory streams is crucial in helping us organize our surroundings as well as listen to music. So music makers and composers have known for a long time that these acoustic features influence perceptual coherence. Melody, for example, is by its nature continuous, but composed lines often don't cohere in time. And either in the moment of a single melodic break or by producing a texture where it seems like there's more than one voice or melody happening at the same time, despite there being no concurrent tones. And this texture is called compound melody, pseudo-polyphony, or implied polyphony. And just to read this definition together, implied polyphony is a musical texture in which multiple voices or melodic lines can be perceived despite the absence of concurrent tones. And this texture is often talked about in reference to Baroque instrumental music, where it's often found. So, for example, one kind of particularly clear implied polyphony is called pedal point implied polyphony. I have a visualization to help sort of concretize what it is that this texture is. So notice in this visualization, there's going to be no tones that are happening at the same time, but it'll sound like there's multiple melodies. Like in here, or especially here. Okay. So, Stacey Davis, who's a music theorist, in analyzing Bach's music, found that there are a few different types of implied polyphony that he was using. And pedal point was one of them, but all of the textures don't need to be quite so fast. So this is an example of what she calls linear implied polyphony, where here you have potentially two implied voices, one that I've just marked in blue and one that's in a lower pitch range and it's marked in yellow. And she calls this linear because each voice is following a stepwise motion within its own pitch range. So let's just have a listen to this. It's slower and more ambiguous. Okay. So here's another example of linear implied polyphony where you have a lower and an upper voice, and they're differentiated by not only their pitch range but also their motivic content. So here you have a lower voice playing a different motif than the upper voice, and you can imagine that if there's an upper and a lower voice that have the same motif, that might be especially perceptually ambiguous. Even less straightforward is when implied polyphony overlaps in pitch range. So here's a type of implied polyphony called motivic implied polyphony. You have two voices, one in the first half of each bar and then the other in the second half of each bar, and they only differ by the organization of the pitch. And finally, you have antiphonal, where it's not really clear how many voices there are, but you have a single motif which is cascading over time. And what differentiates one potential voice from another are these pretty big intervals, as well as a stepwise motion within each motif. So I think implied polyphony is really interesting because it's a very ambiguous space for listeners and has high potential for performers for a lot of different kinds of interpretations. And Albert Bregman, who's a highly regarded researcher in auditory scene analysis, weighed in on implied polyphony at multiple points in his writing, and this is one of those occasions. I'm going to read through the quote with you. "Rapid alternations of high and low tones are sometimes found in music, but composers are aware that such alternations segregate the low notes from the high. Transitions between high and low registers were used by the composers of the Baroque period to create compound melodic line, the impression that a single instrument, such as a violin or flute, was playing more than one line of melody at the same time. These alternations were not fast enough to cause compulsory segregation of the pitch ranges, so the experience was ambiguous between 1 and 2 streams. Perhaps this is why it was interesting." And he says at some point else in this book something to the effect of, it wasn't like composers were trying to get 2 instruments for the price of 1. It was an interesting perceptual organization for the listeners. And I like these quotes because they really relish in the ambiguity. So, which brings me to the first 2 studies, which were EEG studies of neural representations of these textures resembling some of the types of implied polyphony, and collectively looked at how 1 or 2 melodic motifs alternating between lines affects the neural segregation of those lines. So the first study deals with the listeners, and the second study looks at the performer's perspective, and we'll start with the first study with the listener's perspective. So both use EEG as the primary tool. So I'm going to go through and explain a little bit more about EEG and why we used it. It's a non-invasive technique that measures the electrical activity of the brain at the level of the scalp. And the reason it's a good tool here is because it's highly temporally sensitive and allows for a lot of detailed analysis for the latencies of stimulus processing, which is particularly good for stream segregation because your brain is processing that kind of music very, very quickly. So your brain throws off a relatively standard electrical pattern over the first several hundred milliseconds after hearing an event, such as a tone, called an event-related potential, or ERP. And it also has a mechanism by which it tracks a stream of sounds, creating predictions for what should come next. And when at a pattern it is tracking slightly changes, the event-related potential, or ERP, looks slightly different and can reflect an updating of the predictive model about what sound is coming next. So say we have a stream of tones coming in and they're all the same in some acoustic feature, say frequency, and every once in a while we change the frequency of that tone. In this context, we're going to call the changed tones deviants and the regular tone standards. And we can see in the ERP that you're processing, you may be processing the deviants differently than the standards. So here's a plot of some of those ERPs overlaid. So since EEG is measuring electric field, we have a wave over time. And the blue line might be the ERP to the standard. The green line might be the ERP to the deviant, and you can subtract these two and get a difference wave. And this first big negative dip in the difference wave between the standard and deviant is called a mismatch negativity, or MMN. And there's a few, well, one other way we can represent the MMN is through a topographic map. So this plot here might represent just a few electrodes, an average of just a few electrodes of this topographic map, but we can look at the whole head, and this would be a plot of this red difference wave. So around the time of this peak, you can see there's a big negative area here. That's the MMN. So the MMN can reflect changes in low-level acoustic features, such as frequency or spatial separation, but it can also track changes in patterns. So if you have an abstract pattern of tones and then the pattern changes, you might get an MMN. And finally, the MMN is strong when the memory trace of the standards is strong. So if you have tones or a pattern of tones that's happening very infrequently in time, you can imagine that your prediction might not be as strong. So then if that pattern changed, the MMN also wouldn't be as strong. The MMN is also automatic. You don't need to be paying attention to the stimuli for the process to happen. That said, sometimes attention gets involved, and we see that as a later deflection in the ERP. You can see it here too. We call that a P3A. It's a positive wave happening 200 to 300 milliseconds after the detection has occurred, and it represents sort of an involuntary capture of attention. It can take the output of the MMN kind of as input. First the MMN happens and then it grabs your attention and you have this P3A, or it can happen on its own. So studies have looked at if MMN can reflect multiple concurrent streams, and using music as an example, Fujioka 2005 and a couple of other studies looked at if when two melodies are playing at once, to what extent are these two lines encoded separately in auditory memory. So they have this 5-note pattern where first 4 notes are always the same, and the 5th note either ends in a standard terminal note or 2 kinds of deviant notes. So the 2 kinds of deviant notes all happen in the upper line, they also happen in the lower line. And what they were looking at was MMN strength to the deviance in the upper voice in comparison to the standards in the upper voice, as well as deviance in the lower voice in comparison to deviance standards in the lower voice. And so this plot is showing, it's all highlighted with the carrots, or shown with the carrots is all MMN. And for both sides of the brain, for the left and the right hemisphere, for the upper voice deviance and the lower voice deviance, as well as for both kinds of deviant notes, so an in-key and out-of-key note, what you see overall is that we have an MMN in all cases. So this was suggesting that multiple concurrent melodic lines can be represented in parallel in auditory memory. What you also might notice about this plot is that the upper voice MMNs are larger than the lower voice MMNs. So from this, they concluded that the high voice is more salient in this auditory memory trace than the lower voice. So while in music, voices often occur simultaneously, in implied polyphony, they don't. So in this first study, we wanted to see if when a motif alternates between an upper and a lower voice, first, is it encoded into 1 or 2 memory traces? And if a lower voice motif shares the same template as the upper voice, what happens is it potentially even more perceptually ambiguous. So in our study, as in prior studies, the standards were a 5-note group, and importantly, the standards always went down at the end. The deviance instead went up at the end. And today I'm going to talk about 2 conditions in this study. In the first condition, we had these motifs in 1 pitch range, and this is an example of what that condition sounded like. Okay. Then in their next condition, we took every other motif and moved it down an octave to make it seem like we have these 2 implied lines. Okay. So if your brain was tracking this into 1 memory trace, you can see that the rate of stimulation is the same as in the 1 pitch range condition. So if that were the case, we would expect comparable MMN strength in this 2 pitch range condition compared to the 1 pitch range condition. And if that's not the case, as these dashed lines are suggesting, then within each voice, the stimulus rate is twice as slow. So you might expect a weaker MMN. So what did we find? The plots that I'm showing you are the difference wave and the time period for which the difference wave was significantly different between the standard and deviant ERPs, and as well as this topographic map for the period of where it is significant. So as you can see, for our 1 pitch range condition, we have a significant MMN as expected. For the upper voice of this 2 pitch range condition, we have a significant MMN that was comparable in strength to the 1 pitch range condition. And in the lower voice, we had no MMN, but just a later P3A. So what overall this was suggesting was that since the strength of these 2, the upper voice of the 2 pitch range condition and the single pitch range condition were comparable in strength, the lower voice must have somehow been contributing to this upper voice memory trace. But that said, the lower voice didn't receive that same prioritized encoding. That said, attention still got involved because we have a P3A. That template and the deviant notes are recognized by the later working attentional processes, but not the same prioritized encoding as MMN. So we conclude here that there's partly shared neural resources when a melodic motif is shared between implied voices. And we see this asymmetry in encoding of an upper and a lower voice, with MMN present in the upper voice and P3A present in the lower. So this paper is out, and if anybody chooses to read it, that would be such a joy for me. Really, I just want to point out some of the differences, again, between this study and the Fujioka et al. 2005 study, where we have implied lines, so there's no concurrent tones, but we also have the same motif that's shared between lines, whereas in Fujioka et al. 2005, it's the same motif between lines. So this was suggesting that this melodic identity that's shared between lines had something to do with this particularly asymmetrical balance that we found. And that's where we're going next in this next study, is very explicitly testing the segregation of lines when a melodic motif is shared or not shared. So as I motivate this next study, I want to reference some of the examples from the introduction again, and particularly point out the title of antiphonal implied polyphony. So the reason that that title was originally chose by the music theorist who came up with this taxonomy of different implied polyphony types was in reference to a performance practice whereby parts of an ensemble or parts of a choir are trading off the same motif. So we call that antiphony. And so, right, there's a sense that even though that's not strictly implied polyphony, you have a sense of multiple voices, even though there are no voices singing at the same time, just because this motif is passed between performers. So, in this next study, we're looking at performer's perspective and investigating through a two-person EEG study their tracking of the lines when they're either sharing a similar or dissimilar melodic motif. So since we're dealing with performers now, and their actions involve very long-held representations as well as expectations about what their actions are going to produce, we're looking at a slightly different set of ERP components. So I'm going to take a little time and go through what those are now. So in any activity we do, whether you're cooking with a partner, whether you're being on a rowing team, or whether you're playing in a music ensemble, you're monitoring the actions of your partners and you're trying to coordinate with them. And during this monitoring process, we build up an expectation of what our partner's actions are, and we can see a neural response reflecting a prediction error in case the outcome of your partner's or your own action isn't what you expect. And this ERP deflection is called a feedback-related negativity, or FRN, and it's not wholly incomparable to an MMN. So an MMN reflects a prediction error within a sort of locally rule-based context, whereas a feedback-related negativity sort of represents a longer-held expectation of some outcome. This figure is from a Trends in Cognitive Science paper that was summarizing the FRN as well as other ERP components and in response to action outcomes. And in this plot, the blue line is representing a more parietal wave, and the red line is representing more of a frontal wave. And so you can see the first big negativity, in this case, the negative is pointing up. The first big negativity is your FRN, and it's followed by a frontal P3A, which is the same as in our prior study, as well as a more parietal P3B, which is representing further cognitive processing related to memory encoding or potentially alteration of a behavioral response. So when monitoring actions, right, you're monitoring both your own, potentially your partner's, or if you're working with a partner, some joint outcome. And differences between the FRN, P3A, and P3B in these different agency contexts have been observed across several studies. So, for example, in this study was looking at, in this study, the setup was that there was a person playing a gambling task with a computer partner, or they were watching a person play that gambling task with a computer partner. So they would have an action, there'd be some expectation about what the outcome was going to be, and it may or may not be met. And these three lines here, the three bars over to the right, are representing the FRN amplitude of a watching player, either watching the outcomes of the computer partner or the human and the computer that are playing that game. And you can see that the FRN is a lot bigger to the outcomes of your own actions when compared to anybody else that you might be watching. So we can also look at musicians' expectations about what their action outcomes might be. And in this study, they recruited pianists. And how it is that they elicited this FRN P3 complex is by changing the pitch of what the pianists expected to hear. So if you're a pianist, you're playing on a MIDI keyboard, and the MIDI pitch is altered, right? You have a very long-held representation about what pitch you're expecting to hear, and not hearing that pretty reliably elicits this FRN P3 component. So in this study, they had the pianists playing and listening to those sequences that they had played. And in the playing condition, there's a fairly robust FRN P3A and P3B. And then when listening, it's a little hard to see in this color scheme, but the FRN and the P3A are still there, a bit weaker, and the P3B almost disappears. So this is suggesting that within the context of a performer, the FRN during playing is larger than the FRN during listening. And you can look at it in the context of joint action. So this was a study where they had two pianists playing a duet together. One pianist played the left hand, the other pianist played the right hand, and they were playing simultaneous notes. And this study found that the FRN between whether a pitch alteration was in your own part or in the other person's part were equivalent. So in the case of simultaneous joint action, right, you might have equivalent outcome expectations of your partner's part as well in compared to your own. So one more study to set up what we did. It was not an ERP study, but in the study they had people watching a kinematic model of somebody throwing a ball. And the model was either similar to the person's own kinematic motion, or it was dissimilar. And the person's task was to watch this model throwing a ball and say the time point at which the peak of the motion occurred. And they did better at this task. They were more accurate when the model was similar to their own motion. So from this, they suggested that observers of an action use a model of their own kinematic production to generate predictions. And this raises the possibility that online predictions of action outcomes could be modulated when the similarity of an action sequence between an observer and a performer are manipulated. So among the next questions for the next study is, will neural performance monitoring ERPs reflect the similarity of action sequences of a similar or dissimilar motif when alternating between partners? And will performance monitoring of the self be stronger than that of the partner? So in the previous piano duet study, they had equivalent FRNs during simultaneous action, but here we're alternating. So we're going to see what our outcomes were. In this study, we had, it was a piano duet study, and in half of the trials, you were playing across from another human partner, all the while having both your behavioral data, your key press data, and EEG recorded. And in half of the trials, you were sitting alone and playing with a computer partner. We had them play two different kinds of melodies. So in this top kind of melody, they're trading for the first 4 bars a similar melodic motif. And that's what this sounded like. So player 1, player 2, they're trading off the first 4 bars. We also had them play dissimilar melodies. And let's just, for the sake of completeness, listen to that one too. So we used the same tactic as the prior studies in that we were manipulating what pitches they heard, even if they were playing the correct notes. So I want everyone to follow along with me for a second. And I'm going to play an example of this melody with the altered pitches. And it could happen on any one of these gray notes. We don't know which one it is yet. But pretend on whatever instrument it is that you play, if you play an instrument, that you're either player 1 or player 2. And just, if you can pretend as if you're playing, it makes it very real what it was like being in this study. And we told pianists that there's going to be pitch alterations, but please continue on with your part. So, everybody ready? Okay. So everybody, there was an altered pitch. In fact, there were 2. So there was one in your part and there was one in your partner's part. And for every trial of this study, in all conditions, that was the rate of our pitch alterations. So we hypothesized overall that FRN and P3A would be larger in response to a pitch alteration in your own part compared to your partner's part, and as well as that they would be larger when you were sharing a similar motif as your partner. So what did we find? Here I'm showing the ERPs to the notes that are correct in blue, altered in green, and this red dotted line is the difference. And this is a rather large set because we have both both altered pitches in response to your own part as well as your partner's part in similar and dissimilar conditions, as well as with your human partner or computer partner. And you can see the topographies. In this case, we're just showing the topographies for this purple shaded area, which is the FRN. And you can see that even just looking at the topographies alone, overall, they're larger in response to pitch alterations in your own part compared to your partner's part. And if we look just at, I'm a little frozen here for a second. Oh, there we are. Okay. I didn't give anything away. If we look at the amplitude values just for the FRN, we have a main effect where they're larger in response to your own part compared to your partner's part. And we see, sorry, my computer's not behaving right now. Okay, if we add the topographies for the P3A, we still see that there's a main effect where P3A is larger in response to your own part compared to your partner's part, and also a main effect of melody type. So overall, P3As were larger when you were sharing a similar motif as your partner compared to a dissimilar motif. And this was a main effect, meaning that they were larger regardless of whose part it was in. It wasn't just a larger P3A in response to your partner's part, right? So overall, when you were playing a similar motif, you had a larger FRN. Sorry, you had a larger P3A. Let's see if I can move on to the next slide. Good. And I wanted to show our P3B results, which fairly clearly showed that you have no P3B in response to your partner's part, but just a P3B in response to your own part. And this makes sense and is comparable to what the study had found, where they just had pianists either playing or listening. And if P3B does have to do with behavioral decision making, you're only acting in your own part. That's the only behavioral part you're accountable for. So in this alternating context. So as predicted, performance monitoring processes were modulated by agency with greater pre-attentive and attentive resources devoted to self-generated feedback rather than to other generated feedback, as indexed by our FRN, P3A, and P3B components. So thinking about that previous piano duet study, we can think that unless entirely synchronized action is required, our results are showing that performance monitoring of one's own actions is distinguishable from and more salient than that of a partner's. We also found this larger P3A when you were playing a similar motif compared to a dissimilar motif. And since this is, like as I said, it's a main effect, there's a few different possible interpretations for this result. It's possible that sharing a sequence with a partner is increasing some motivational saliency of generally having your own part being mimicked. And this motivational saliency is known to affect P3A amplitude. It could be that it's also just increasing the saliency of that pitch in your working memory. You're hearing that melody twice as much, so therefore your attention is grabbed when there's a pitch alteration more than if you weren't hearing it as often. And it could be that we found the P3A effect, but not effect of similar or dissimilar melodic motif for our FRN, right? We didn't have that effect for our FRN results because the FRN could be, in the case of pianists, really just representing these very long-held action outcomes. The pianists we recruited for the study had been playing for a while, and we basically might have hit a ceiling effect with the FRN, that it's just not sensitive enough to these kind of in-task manipulations of a single melodic motif than it is just, I'm expecting a certain outcome when I hear a pitch, and that's not what I'm getting. One potential limitation of the study is that everybody had played all of the parts. So we had played, I was player 1 and you were player 2 for half of the trials, and then we would switch, and I would be player 2 and I would be playing, I would be listening to the part that I had just played. And you can imagine that if you're playing a melody over and over again, that you might develop a kinematic representation of what it's like to play that melody, and then when I hear you play it, right, I might have a different expectation about, how do I say it? I might have a better representation of those actions and therefore a different ERP deflection pattern. So that's something to think about. And there's an effect that we found that I don't have time to talk about in the talk itself, but if someone wants to ask me during the question and answer session, I would be very happy to talk about it, which was relating the amplitude of the FRNs to the pianist's trait empathy levels. So they took an empathy questionnaire and we found a relationship between FRN and how empathetic they are. Okay, so now we're on to study 3, which is somewhat of a departure from the previous 2 studies because it's not an EEG study. It's looking at performers' timing and motions. And as I said in the introduction, a common and iconic form of implied polyphony is when you have a single performer that's playing one monophonic line that seems to break into these multiple streams. And bringing out these implied voices is of great importance to the people who play music that has this texture in it. And I have a quote from a well-known violinist, Yehudi Menuhin, and he's talking about the Bach violin sonatas and partitas and the cello suites. And again, I'd like to read through this quote with you. He says, "But certainly the most important thing is to observe the clear and clean contact of the individual voices. This also applies in the many movements in which there are only one. This also applies in the many movements which there are only one voice, for that is only a superficial aspect. For instance, although many of Bach's movements for solo violin, and particularly for cello, are written in one voice, that is, without counterpoint and harmony, the counterpoint and the harmony are in fact implied, and every effort must be made to bring the different voices out clearly. The minor inflection, the minimal deviations, are absolutely essential to the sense of the living work." So musicians have a lot of expressive tools at their disposal to bring out these lines. So this study was an investigation into 2 ways that a performer might reflect a melodic grouping that's associated with implied polyphony. And for the purposes of the manipulation that we did, we were using a scoring method that was used by Stacey Davis. When she was creating her taxonomy of different implied polyphony types, she wanted to systematically know where is it that a single melodic line might break into multiple streams. And she based this scoring method off of 3 rules related to pitch organization. The first rule is just identifying the size of an interval. If it's a large interval, it's going to be considered as a potential stream segregation point, and if it's larger, it's going to get more points. So this is just an example of a few points in this passage that might be identified as potential points for segregation. In the next rule, you're looking at the direction of approach and departure from that interval. And if the direction of approach and departure is the same, it's less likely to break up into multiple streams, and so you don't add any points. But if the direction of approach and departure is different than the direction of the pitch interval itself, you'd add 1 point each for approach and departure. And finally, if you have a large pitch interval that's in a sea of stepwise motion, that's going to seem very salient as a potential place for a voice break. And so here you'd add a point for every contiguous stepwise motion around a large interval. And so I want to note again that this wasn't made to be an explicitly perceptual model. There's no ceiling to these scores. The first and the third rules you can add as many points as you want, but it's just a general method to identify points where a single melodic monophonic line might break into multiple voices. So broadly, music performance research has looked at how conceptual melodic groupings are reflected in performers' timing, and called microtiming when dealing with smaller groups of notes. In this case, this is another study by Stacey Davis, where she was looking at performance timing of these violinists playing this passage of music. And this plot, each point represents a value relating to timing on each note. And 0 is representing the average duration of the 16th note for each performer. So some value up at 100 would mean that that particular note was twice as long as what that performer normally plays. And you can see that this passage has a single ascending melodic sequence where the ascent is noted by a large interval jump. And most but not all violinists take time at these interval jumps. So, excuse me. There's variation, and that's celebrated, right? They can play it however they choose, but they might choose to take more time. And while timing and other aspects of their sound are very important to performers, their structural interpretations can also be evident in the motions that they make. And something that's been fairly well documented is that performers can embody their representation of phrase. So on the higher hierarchical level of the phrase, we can see it in performers' motions that there's a periodicity reflecting a repeating phrase. And here is a selection of a figure from one of the studies that was showing this. They had a pianist, they had a set of pianists, 9 pianists. Here's 2 motions from 2 of them playing a Chopin prelude. And all of the pianists had agreed about where the phrasing structure was for the Chopin prelude. And here it's represented by these blue lines. And the red line is a representation of their upper body motion. So even though these 2 pianists are moving differently, you can see that there's this semblance of periodic motion that generally reflected the phrasing structure. And in another study that we had done, we asked cellists to play this short passage of music with 2 interpretations that we prescribed for them. It either had short groupings here, where these gray bars are representing where the short grouping boundaries were, or it had a couple of long groupings, so more like thinking of a long phrase. And this black time series is representing just the up-down head motion of the cellist. And the reason we were looking at head motion is because it's not as strongly related to what they need to do to play the instrument, and it's a freer part of the body. So we wanted to look at here, do they embody it above and beyond what they need to do to be able to play? And here's just 2 of the takes from 2 of the cellists. And even though the motion of the cellists overall reflects a different pattern, you can see that there's fewer peaks represented by these carets when the cellists are thinking long groupings compared to short groupings. So we're getting at kind of a lower hierarchical level here than in this phrase-only study, and a single melodic break is fairly low level. So to summarize, pitch factors related to implied polyphony can create a local segmentation of the melody, which is related to perceptions of discontinuity in an otherwise continuous melodic line. Since performers embody musical discontinuities on the level of a phrase and can embody smaller groupings, performers may embody local discontinuities produced by organizational pitch factors related to implied polyphony. And our study goal was to explore and illustrate the extent to which performers embody discontinuities reflective of implied polyphony, independently or above and beyond what they may do to indicate the local discontinuity in their sound. So following existing research and also the kind of the canon of pieces for which implied polyphony is often found, we recruited violinists for this study. And they played this excerpt of music, which was from a Bieber sonata. And there was a few passages that were modified. There's 6 shaded passages here, and they represent 3 pairs of segments. So paired segment 1, paired segment 2, and paired segment 3. Within each pair, there's a strong discontinuity and a weak discontinuity. And strong discontinuity means that it had a pretty high score in that scoring method I was talking about. Weak means that it had a pretty low score. And if I can bring your attention just to segment 2, you can see that there's an interval in here that's indicated in brackets. I'm calling that a critical interval. And it's exactly the same within this pair. And notably also the strings directly before and after the interval that the violinists were playing on were exactly the same. So we achieved this difference in score or potential for a melodic voice break by just changing those 2 later rule factors that I had mentioned about direction of approach and departure and amount of stepwise motion. So we had the performer's timing. We extracted performer's timing of every note that they played. And these were our results for all 6 of our violinists. We had them play it twice. So we have take 1 and take 2. And we have here the notes for segments 3, 2, and 1. And overall, right, you can see that performers were generally, not everybody, but they were generally taking more time at the first note of this critical interval during strong discontinuity segments compared to weak discontinuity segments. And the size of this effect didn't change across the 3 different segment types. We also recorded their motion. So they had a lot of different body markers on, as well as a bow that had 3 markers on and 2 on the violin. And we reduced this down to a subset of body markers that we were going to analyze. We have 2 takes for each violinist. And so to holistically characterize the motion of the body, we used a principal component analysis, which transforms the data into a smaller set of uncorrelated time series. We can map these principal components back onto the skeleton to interpret what they mean. So this audio that you're going to hear also is resynthesized, but it's reflecting the onset timing of the actual violinists. So it's a physical model, and there's no vibrato. Our violinists played with vibrato sometimes, but just in case you're surprised, that's why it sounds the way it does. So over on the left, you have the original motion, and then principal component 1, 2, and 3. And as you're watching, if you want to sort of characterize what it is that those motions are representing, I'll tell you what my interpretation was in a moment. Okay, these were mine. Okay, so the violinists were moving differently, but a lot of them had this side-to-side motion, which represented a fairly sizable amount of the variance in those markers. So this is what we were analyzing afterwards. And what we did was, for the duration of every note that they played, we made summary statistics of these principal component values. And where some pattern came out was in the velocity on each note of that side-to-side motion. So this is a similar plot from before, take 1 and take 2 for each segment. And the velocity of the side-to-side principal component on each one of these notes. And there isn't as strong of a pattern, right, as compared to our rubato results. But what did come out that I wanted to point out was that in segment 3 in particular, if you look at the velocity just on this middle note here, it's the first critical interval, there's not really a noticeable difference between the strong and the weak discontinuity segments. Whereas even though it's subtle, in segment 1 and segment 2, our PC values are more negative during the weak discontinuity compared to the strong discontinuity. So it's subtle, but it was there. That said, it was subtle enough that we wanted to follow up and do another study to see, is this kind of motion perceptible? So we ran an online study, and people were looking or listening to these 5 note segments. And they heard every segment from every performer once, and their job was to say, how many groups of notes was the violinist expressing? This is the question they were answering. And they could either say the violinists are expressing 1 group of notes, or they're expressing 2 groups of notes for each segment. And they were randomly assigned to one of these 4 groups, listening to audio only, having video only, having audio visual with the full motion, or audio visual with these non-technical, mostly the side-to-side motions, subtracted out from the motion. So it still looks like a violinist, they're just not moving as much. Okay? So we have these responses which are binary. It's either 1 or 2 groups of notes. And we have 2 kinds of segments, our strong discontinuity and our weak discontinuity segments. And we gave each participant for each trial 1 point if they said, I think that the violinist is expressing a strong discontinuity, and the violinist, if they said that the violinist was expressing 2 groups of notes and the segment underneath was a strong discontinuity, we gave them a point. Likewise, if they said, I think the violinist is expressing 1 group of notes and it was a weak discontinuity, we gave them a point. But otherwise, they got no points for that trial. So in the end, we ended with this percent matching score for each person in our study. And as you can see, overall, the performance was fairly modest. I think this can be a difficult task for people. But what came out was that only in the conditions that had full motion, in our video only and in our audio visual full motion segments, was there a significant differentiation in these percent judgments between segment 1 and segment 3. And notably, segment 3 had overall a lower percent judgment matching than segment 1, where at least we had seen by objective analysis there was some differentiation in motion. So whether or not it was exactly what we had found in our objective analysis, or if it was something else, right, some potentially smaller motion that some of the violinists were showing that our participants saw, it suggests that only full motion, these non-technical motions, are differentiating judgments between segments. So overall, violinists generally took a greater amount of time at the start of a strong compared to a weak discontinuity. And this has been shown before in the literature, but we were very controlled in the way that we were showing it, so this is good to see. They also had a variance in how their non-technical motion was representing these different discontinuity types. And while we found that velocity and side-to-side motion provided information above and beyond their microtiming, it was perceptually subtle, right? So in this second experiment, it wasn't as if the people who saw the violinist's motion suddenly got a lot better, you know, if they, or the opposite, you know, if the motion was somehow detracting from the clarity of the groupings that the audio was presenting. But it did sort of differentiate some segments from each other more strongly. So despite these segment differences and the subtlety, also the controlled paired segment design that we had allows, I think, for the suggestion that performers occasionally will embody these kinds of local discontinuities. And we tried very hard to keep this as an ecologically valid study. We drew from a music from which this kind of texture is commonly found. And violinists were free to interpret it however it was that they wanted to. So in our previous cello study, we told them, these are exactly the groupings they are. Please use these in your interpretation. But here, they just had a blank canvas. They didn't see those shaded bars. So they were playing how they wanted. And so that also contributed to the subtlety. They were free to interpret. So in conclusion, Study 1 provides neurophysiological evidence for the use of partly shared neural resources when a motif is shared between implied lines. And particularly, we saw this asymmetry in encoding between an upper and a lower voice, which was stronger than what prior studies have found. And it's possible that melodic identity had played a role in this asymmetry. Study 2 demonstrated that during performance, whether a melodic motif is shared or dissimilar between performers is reflected in their neural performance monitoring. So P3A, right, was larger during similar melodic motifs than when pianists were playing dissimilar melodic motifs from each other. And I'm particularly proud of this study. It was a big team effort, and there'll be lots of thanks during the thank you slide. But it was very ecologically valid, given that it's an EEG study in which you need, you're trying to have your performers not move all that much. But we had them playing a task that's fairly common in musical performance, that you'll trade off a line that's similar or dissimilar from your partner. And I think it underscores the sense that joint music making as a paradigm can be really helpful in studies of social interactivity. And finally, Study 3 showed that performers' timing and motion can reflect pitch factors beyond interval size that indicate a change in implied voice. And if you'll humor me in reading sort of the entire thing together, the presence of one or more motifs is impactful in neural representations of multiple implied melodic lines, and performers' interpretations and expression of pitch organization related to implied lines is reflected in microtiming and subtly and variably in motion. So where does this work go from here? The first two studies had very specific motifs at a specific pitch range and a specific timing. And to be able to relate this back really to the very broad kinds of textures that are seen in music, and as I showed in the introduction, we would want more studies like this, varying factors like motif length, pitch range, tempo, to really be able to relate it back. Implied polyphony is something that happens over time. So in this last study, we're looking at single melodic intervals, but usually implied polyphony happens over multiple bars, or at least a larger segment of notes. And so I think looking at performers' expression of the kinds of textures that are more commonly found over time, say like a sequence, could be really neat, looking at how performers embody it. So if there's more than one voice that they're trying to introduce, maybe they show it strongly in the beginning, but they don't need to show it at every voice entrance in the rest of the sequence. So that I think could be a really fruitful direction. And concurrent polyphonic textures are also really challenging for a listener. So if you have multiple voices that are happening all at the same time and they're all of the same timbre, it can be very difficult to pick a voice out of that texture. And I think looking at performers and how it is that they might be showing voices that are otherwise hidden could speak to both their interpretations and representation of an otherwise complex musical structure and into an audiovisual interaction from an audience perspective. So we're now to the thank yous. First and foremost, I want to thank my advisor, Takako Fujioka, whose mentorship has gone above and beyond. So she freely offered her expertise at every stage of my PhD and really taught me so much. And she's edited so many words. She didn't edit these. I spared you these. I'd like to thank the rest of my committee, Dr. Eve Clark. So It was in your class that I piloted that cello study, and now it's a published piece of research. So I'm so appreciative that you are here and able to share this today. It's so meaningful. I'd like to thank Jarek for stepping in at the last minute. I look forward to hearing your questions and a fresh perspective on this work. I'd like to thank Jonathan for, again, being here at every important milestone for me. So for Qualls, my SAE, and here today. And you always have very insightful comments, and I look forward to hearing them after. And I'd like to thank Chris for, again, being a great mentor. You've been here the whole time, and I just really appreciate the work that we've done together. Like I said before, the Piano Duet project was a big undertaking for many people. And so I'd like to thank Tyson, Chrissy, Iran, Nick, Wissam, and Matt, who are really a core group there from the beginning. Tyson, Chrissy, Iran, Nick, and Wissam were in Music 451C, and this project was an outgrowth of that class. And they had a lot of brain power put behind the design of the study and lots of details and being able to recruit and do data analysis as well. And a big special shout out to Matt, who also supported the project at all stages and had so much help in creating the Max MSP patch that ran this study. Thank you so much. I'd like to thank Amanda Lauren-Sussman, who had helped with data collection over the summer. It's a study that requires 2 people to run it, and so she got a chance to do research in the lab, and it provided a much needed extra pair of hands. I'd like to thank Dr. Ari Washburn for being so interested in this study, and you know, she's looking at a whole nother side of the data set, and I really look forward to seeing everything that comes out from that. And I'd like to thank Jay and Sasha for also helping and providing technical expertise in getting things running in the lab. I'd like to thank everybody who I've gotten a chance to work with or alongside in the lab. You guys have made it a very vibrant place to be, and I'm very appreciative. The violin project also had collaborators. Stacey Davis has helped contextualize her work and has provided invaluable advice in developing this study. Julius was helpful in creating that, in getting the physical model working to be able to revive our audio from the violinists. And I'd like to thank my cousin and neuroscience student Julie, who spent many hours in the lab with me last summer helping to process that motion capture data. I'd like to thank everybody at CCRMA, and apologies if there's anybody that I left off of this list, for making CCRMA a safe and productive place to work. I'd like to thank the Jabal family and VPGE for providing funding for my last 3 years and summer funding, which has made a big difference. I'd like to thank all of you for being here and for being, you know, a part of the CCRMA community, which I know we all appreciate so much. And I'd like to thank my friends. I had a friend who traveled out here today, and I'm so appreciative. And my family and everybody who's watching online. So, you know, this was a big group effort to get this work done. And I look forward at this point to taking your questions. Are there any questions? So, to relay what will happen next, there's a period for public questions, and after the public questions are over, anybody who would like to stay is very welcome to a reception. We'll have a little break, at which point then I'll meet with the committee, and we'll figure out a way to, we'll either call or Skype you in, Jarek, and then I get questioned by the committee. And then they vote. So I'm welcoming questions either from the committee or from anybody else who wants to ask me one now. And if you are online and you have a question, you can type it in the chat box. Yeah, Ben.
Can you talk a bit about the relationship you found between the empathy measures you were talking about?
Yes, I can. In fact, it's my next slide. So as I mentioned, the pianists had taken this empathy questionnaire. They answered around 40 questions related to how they relate to others, and higher scores tend to indicate people who have a higher level of trait empathy. And what we were expecting to see was that people would have a larger response to their partner's part if they have a higher level of trait empathy. And that's not what we found. So there was no correlation between FRN amplitude and the other person's part, but there was a correlation between your FRN amplitude to those alterations in your own part and your own empathy score. And so we spent a lot of time scratching our heads about this and trying to interpret it. And there are a couple different interpretations. One is that even if necessarily those resources weren't directly going to processing your partner's part, it could be that people who have higher levels of trait empathy in this kind of musical duet context are less strongly monitoring their own action outcomes. And there was a couple of other studies that were interestingly showing a relationship specifically between FRN and the evaluation of negative feedback, and how when an action outcome is, or some general piece of feedback is specifically related to a person's sort of goals, that an FRN is more suppressed. So we're changing the pitches on these pianists, and it could be that they're not viewing that as a positive outcome. And so therefore, it could be that this higher empathy level is related to kind of just a decreased processing of this, in this case, potentially interpreted to be a negative outcome. So that was how we explained that. And thank you for that question. Are there other questions? Chet.
A very basic question from someone who doesn't know his neuro stuff very well. I guess whenever something unexpected happens, I do expect to see a spike, but why is it generally a negative? For the MMN.
That's a great question. So I'm going to think about that for 1 second.
It might even be a very big question.
Yeah, I mean, I think it's something that it's probably a question I could have asked my second week here, and you know, I mean, so EEG is reflecting a different pattern in the electric field, and so you have neurons that are firing in a different direction. It's creating a different pattern, and I think it is interesting that in both cases it's negative, and that's what I've talked about. I'm trying to think if there's other examples where there's an ERP deflection that's representing an early evaluation that wasn't the outcome that you expected and it was positive. And I can't think of one, so I'm not saying that there aren't any. They're just not coming to my mind. It's a good question, Chet.
Thanks. Also, your PCA experiment was awesome. That was really
I'm glad
cool.
you think so. Yeah, I can share the toolbox that helped to make all those visualizations and stuff if you want it, in case you're ever working with mocap data.
Oh, I'm not sure I am. I just thought it was exciting.
Just in case in the future. Cool, thank you. Any other questions? Okay.
Oh, I've got a question from Julius here.
Oh, Julius is watching, great.
Julius says, question, how does implied polyphony phrasing differ from normal musical phrasing, or are the same techniques used for both?
Right. So implied polyphony typically happens under the level of a phrase. I think of it as just a lower level melodic grouping than phrase grouping itself. I can't think of an implied polyphonic texture that would necessarily span across a phrase. I think within a particular phrase, you might have multiple implied voices. So if that, it kind of answers a different version of his question, but I think they're kind of fundamentally different structures.
He says thank you.
Good. Owen.
Probably a very boring question, or simple question. What would be one thing that you would like to add to this? So, for example, like, oh, I want to see how this works over like greater physical distance. Say like stuff like Chris is interested in the delay between people and entity. So, any other?
Can you repeat that one more time?
Sorry. What would be something that you would add to this study? Like, what would be a logical next step? Like, say, like, oh, I wonder what happens in a condition where it's a symphony orchestra and we're actually trying to figure out something that includes distance. Do you have something like? Do you have like a special training project you'd like to do with this? That would be the next logical step.
Right. So particularly with the violin project.
Yeah.
Yeah. I mean, so the violinists played this movement of Beaver, but they also played a movement of Bach, and that was specifically to be able to look at implied polyphony over time. And these different kinds of implied polyphony are shown to be expressed differently in different timing patterns from musicians. So they might take more time in one kind of implied polyphony and less time in another. And so to see whether or not in sequences or in textures where they're taking less time, are they instead showing it through motion, or are they moving less? Or in the cases where they are taking more time, maybe that's kind of where their expressive outlet is going. They don't need to show it in the motion as much. So I think looking at that balance or trade-off, if it exists, between embodiment and the expression that's going into a sound. And specifically, since this is already set up in prior work to say that some kinds of implied polyphony are more like inherently expressive than others. That's what's immediately sitting here. So when you say what's next, there's some data to look at. But I mean, we had thought when we had done this study too that, wouldn't it be great if the violinists in the mocap study were sort of set up on the stage? And there's a few examples of kind of lab scenarios where you have an audience and a performer live, and the ability to record all of this data at the same time. And I guess then we would need to wonder why we would want to do something like that. I would need to think about that, but it's a step in a more ecological route. Yes?
Could you give the rationale for why you decided on the duration of the stimuli? So in the violin study, if I understand correctly, the motion study, people were listening to these very short stimuli.
Mm-hmm.
Why were they that length? Because I was thinking, obviously, that's the subtlety, isn't it? If you have more context, it makes it easier.
Yeah.
What your thinking was around that.
Yeah, thank you. We had wanted the segments to truly be pretty much physically exactly the same. So any differentiation between the segments wouldn't be due to anything that they would have needed to do to play the violin. So without changing too much of the surrounding texture, we had picked on these 5-note segments. But that was really the only reason, was just saying, okay, in the immediate context, without changing too much of the piece, how can we make this very controlled comparison? And there wasn't a background study that had informed that segment duration. And a couple of the segments had a longer period by which the motion was exactly the same, but there was a segment for which it needed to be shorter, and so we thought we would standardize it across the different segment types. But maybe what you're hinting at is that it's a particularly hard task, and the segments are quite short, and it would have been great if they were longer. Yes.
Got another question from the chat room from Yarek. Yarek asks, can you expand on your motivations for comparing duets with live and computer partners, and if the results in that dimension you got were as expected, satisfying or final?
Thank you. So the first study that I talked about in motivating that the piano duet project was a study where people were playing a game with a computer partner, or they were watching a human and a computer play that game. And in that study, they found that there was a trending effect when you were watching a human versus watching a computer, that your FRN would be larger to the human than that of the computer partner. And so that motivated us to have half of our stimuli be played with a human partner or a computer partner. And we didn't find any effect, a difference between the partner types. And so how we had interpreted this was by looking at a few other studies whereby the social distance between the partners changed, and the FRN response to a partner changed based on whether you were performing the task with that partner or watching that partner do the task. So to make that concrete, there was a difference in FRN when you were watching a friend versus a stranger do a task. I forget what exactly the tasks were in these other studies. But those differences, the difference between the response to a friend and a partner got smaller when you were playing with whoever that person was. So it mattered less in terms of the FRN amplitude. So it could be that by either playing with a computer or by playing with a human, it's a little fundamentally different, because I don't know what the social distance is between a human and a computer that you've never met. But but basically that distance gets a little smaller in a joint action context. If that answers the question. Okay. There's no more questions? Any more questions? Okay. Thank you again so much for coming. Thank you again to everybody who tuned in online. There's going to be a reception outside. Please enjoy, and thank you again, really, everybody.
Just going to stop the stream now.